In this lecture, I'm going to give an introduction to LiDAR technologies. But we're going to start a little further back and talk about active remote sensing in general, and a little bit about radar remote sensing as well, and how those relate to the use of LiDAR that's becoming more prominent and more prevalent now in the GIS world. So just as a quick overview of this lecture, we're going to start out by talking about passive versus active remote sensing. The last lecture for this course, the last video you would have watched, was about passive remote sensing. Now we're moving into this realm of active remote sensing, where we're actually producing the energy for the imaging to occur, instead of just like detecting that natural ambient energy from the sun. Then I'm going to talk about the principles of LiDAR, what it is, how it works, and a little bit about actually using LiDAR data in GIS, processing the data and analyzing the data. So on the bottom right, we have an example of LiDAR data. This is the Bixby Bridge in Big Sur. It's a frequently photographed bridge, really popular tourist site. And we see a plane flying over. That plane may be emitting pulses of lasers basically at this scene to collect that data like we see on the left. All the remote sensing methods we've talked about so far center on reading values of reflected electromagnetic energy at some point in the spectrum using some sensor that's on board some platform, either an airplane or a satellite. And last week we discussed how sensors, much like cameras, are used to read this information in a similar way that a camera does. It basically reads how much reflected light there is in each of these different parts of the spectrum. Unlike the passive remote sensing that we talked about last week, active remote sensing actually doesn't just detect the type of light being reflected in that area of the electromagnetic spectrum near the visible part of the spectrum. Instead, for active remote sensing to occur, we actually have to produce energy at some point in the spectrum, or another type of energy, emit that energy back towards Earth, and wait for that energy to come back to the sensor. So passive sensors basically read the reflected energy that's originally from the sun. They depend on this visible light. The sun provides light energy. Passive sensors, like a camera, read the amount of radiance or reflectance as that energy from the sun is reflected off of objects. This is kind of like a standard camera without a flash. That's that example on top, in the top right in the figure. Returned light is simply measured based on how much of that sun's energy is reflected off of an object. So trees appear green to us. They reflect a lot in the green part of the spectrum. If you have a sensor that detects those green wavelengths, you'll get like a high value for that reflectance in that part of the spectrum that sensor is sensing. Active sensors emit their own source of energy. So energy is sent out from that sensor as a wave or as a pulse of energy, and then the sensor is able to measure the energy returned. This is more like a standard camera with the flash activated. When you take a picture, energy in the form of light is emitted from the camera, from that flash in the camera, that illuminates the object. And the reflected light that was originally emitted from that flash is what's reflected back to the sensor and makes up the image that the camera reads and produces. Now, translating these principles to like how these different sensors actually work in the realm of geography when they're mounted on a remote sensing platform like a satellite or an airplane, here are simplified versions of passive and active sensors. The image at the top right is like basically a passive sensor. It's just like that camera without the flash. Sunlight is required to light up that town, those buildings, trees, the road. All those things are lit up by the energy from the sun, and the reflectance of that energy makes it up to the satellite, and the satellite reads how much is reflected in different parts of the spectrum, depending which band that satellite uses, or which range of bands that satellite has. On the bottom, we have an example of an active sensor. In this case, energy is being sent from the satellite. That energy reflects off of the town, off the buildings, the road, the trees, and is sent back up to the sensor, where it's read by that sensor and translated into an image. The sensor is probably reading something that's outside that normal visible spectrum. So even though the sun is lighting up that region, the sensor on the satellite is going to be a specific sensor that can read that energy that it's emitting, or read that reflectance of whatever type of energy it's emitting. So the most common type of active remote sensing that's been employed for the last several decades is radar. This stands for radio detection and ranging. So basically, radar is a ranging or distance measuring device. It has a transmitter, receiver, antenna, and a data processing system all clumped together. And it uses pulses of microwaves that are sent out from that radar device Those microwaves are sent out to the surface, and just like light in other parts of the spectrum, just like energy in other parts of the spectrum, that energy can either be reflected, absorbed, transmitted, etc. It turns out that microwaves travel more easily through the atmosphere. Clouds don't reflect them or absorb them, so microwaves can travel right through a cloud. Doesn't matter if they're clouds because, again, this is a different type of energy. While clouds block visible light, they don't block microwaves or radar pulses. So looking at the image to the right, that red line pointing downwards, those red kind of curves being emitted towards the Earth, that's energy in the microwave or radio wave part of the spectrum being emitted from this radar system, makes it down to Earth's surface. Objects on the surface will either absorb that energy or reflect that energy back up. The green lines represent that energy being reflected back up. So just like with a Landsat image, you end up with a raster image of black and white data. However, the colors actually don't correspond to like colors in the real world, like we saw before when we were looking at visible data in different parts of the visible and near infrared part of the spectrum. Instead, what we have here is the amount of that radio, microwave or radio wave energy that makes it back to the satellite. So again, once that energy makes it down to Earth's surface, a couple things can happen. It can bounce straight back up and be perfectly reflected back up to the satellite. That'll give like a really high value for that radio or microwave reflectance. It can also be scattered. That's one of those things we talked about that can happen to electromagnetic energy depending on the composition of a substance. Some things will just scatter this energy in all directions instead of reflecting it. If something gets scattered around, it's less of that energy is going to make it back up to the satellite, so you'll end up with a darker pixel. Finally, just like other objects, that energy can be absorbed as well. Also, if the energy is absorbed instead of reflected or backscattered, you'll end up with a low value there. So the type of radar we use that's feasible from space is what's called synthetic aperture radar. This is a type of radar that can be used over very large distances to get relatively high resolution data. So when you hear about radar being used in the realm of remote sensing, if you hear about radar that's fixed to a satellite, it's generally going to be the synthetic aperture radar. Again, the images that result from synthetic aperture radar aren't going to be like Landsat. You don't actually get like the color that's reflected from an object. You get other properties related to that object. And generally the resolution is lower as well, but it is really useful for a few very specific reasons. Because radar has these really long wavelengths compared to the visible or near infrared part of the spectrum, as I mentioned before, radar can penetrate clouds. Clouds transmit that energy from radar instead of scattering it, absorbing it, or reflecting it. So it's irrelevant whether they're clouds or not, radar can still get a good image of what the ground looks like. In addition to imaging the ground through heavy cloud cover, you can take images of both the conditions during the day and during the night. So you get a larger temporal window with which you can actually image the ground. You can also get accurate distance information. So a lot of that information on elevation comes from radar. Radar can also allow you to measure texture of an object. So if you just imagine like smooth, calm ocean water versus choppy ocean water, when those radar pulses hit that water, if the water's really choppy and those radar pulses hit the water, they might be scattered in all directions. You have higher backscatter. But if you have like nice, smooth, glassy surfaces to the water, you're going to get more effective reflection of those waves. The same goes for other things as well. So nice, fresh, new snowfall might look different than like a glacier with a bunch of crevasses where like the top layer of snow has kind of become misshapen and formed differently over time. So while there are some cool capabilities that radar offers, there are also some drawbacks. The resolution usually isn't as good. You don't get as nice of a picture overall of an area because you don't get this information in the visible part of the spectrum. You can classify things like we've done before in class based on their properties and kind of give them a false color look as what they might look like in the real world, but you don't truly have that like visual information. You'd have to combine it with other data. So because of the differences in texture of different things that these radar pulses are hitting on the ground, you get really speckled images, as you might see on the left right here. There aren't as clear divisions between like different areas with different land covers. And then overall, there's also complex processing. So if you're working with a lot of radar data, there's a lot more to take into account to actually process that data and get it into a form that's nice to look at. But as you see on the right, in a lot of cases, it's really the only type of imaging that you can get. So this is in Ireland in 1991. Ireland's covered in clouds a lot of the time, and with Landsat data only coming around and imaging a region every month or so, you might just completely strike out in the course of a whole year of getting like a nice, crisp, clean image of a place. So by getting a radar image of that area, at least you can have like some data on that area. Here's another practical example of using radar data to image change on Earth's surface. So this image is from Sentinel-1. This is a European radar satellite system. It takes images at a pretty similar frequency to Landsat, so every month or so. But again, this is really useful in areas that are frequently covered in clouds. And one example of somewhere that's pretty much always covered in pretty significant cloud cover is the Amazon, or any tropical region really, during the wet season. Tropical areas get a ton of rainfall, that's why they're tropical. Rainfall comes from clouds. If you want to compare something like the Amazon or any other rainforest, and compare the conditions in the wet season versus the dry season, you might never get a nice clear picture using the visible part of the spectrum of that study area in the wet season because of how many clouds there are. So the radar satellite here allows measurement during the wet season when there are clouds, and also during the dry season when there are fewer clouds. So we can get some finer temporal scale analysis of deforestation in the Amazon, whereas you might usually with like Landsat compare a region over a year or several years. In this case, we're looking at deforestation by gold mining on a seasonal basis. We're looking at like the first part of the year versus the second part of the year. So several areas of interest where it looks like deforestation has occurred due to gold mining just over these short, like 6-month periods of time can be identified using this data and looking at the differences between different seasons. One last note on radar before we talk more about LiDAR. Another common application of radar is the use of something called SAR interferometry. This is often shortened to INSAR. This is when you take two of those synthetic aperture radar images that have really high resolution information on elevation, overlay them, and look at the changes in elevation over time. So you can take multiple passes over the same location at different times to reveal changes between those different times. If you have a satellite that's undertaking the exact same orbit pattern over time, the radar pulses that it sends out will be slightly different if there's been a change in elevation in that location. So we can look at the change in phase at what wavelength is being returned to the satellite, and by that phase difference, find really, really fine scale changes in the elevation of an area. So you can actually look at millimeter scale changes of elevation in an area. This picture on the top right is an example of using SAR interferometry for looking at volcanic uplift. So in a lot of cases, when a volcano gets closer to erupting, it might swell with magma, and you actually get growth of the flanks of that volcano, and this can be measured at a really fine scale using INSAR. You can also look at phenomenon like subsidence. In the Central Valley of California, we've been pumping out a lot of groundwater for agriculture there, and there's been pretty significant subsidence of the landscape there because we're taking water out of the ground, everything else kind of compacts because of the lack of water that used to be there, and you end up with the ground actually dropping on the scale of meters over a decade. But you can measure that at much finer scales using this information. So over the course of the year, you might look at a couple different radar images and compare them using interferometry and these multiple images to see how much change in elevation there's been.